Hey, good morning, everyone. Good morning, good afternoon, good evening. I'm Koji Yamashita, the moderator of this webinar. Welcome to the IEEE Foothills section. Our Foothills section covers a wide geographic area stretching from West Covina to the eastern end of California and from Temecula to Baker. Today, we have two speakers, Dr. Shuchismita Biswas and Dr. Kaustav Chatterjee from Pacific Northwest National Laboratory, also known as PNNL. Welcome to the IEEE Foothills section. Before starting your presentation, let me introduce you both. Dr. Shuchismita Biswas is a power system engineer at the PNNL, where she leads the Sensing and Measurements team. She holds a PhD in electrical engineering from Virginia Tech and has extensive experience in developing measurement-driven application for power systems analysis. Prior to joining the PNNL, Dr. Biswas worked at PJM Interconnection and Schneider Electric. Dr. Kaustav Chatterjee is a power system research engineer in the Sensing and Measurement team at the PNNL. He earned a master's degree in electrical engineering from the Indian Institute of Technology, Bombay in 2018, and a PhD in electrical engineering from the Penn State University, Pennsylvania University in 2022. Dr. Chatterjee's research interests include online monitoring and estimation of power system dynamics, stability assessment, control, and system optimization. So, well, Shuchi and Kaustav, I will stop sharing the screen.
Thank you, Koji. Let me share my screen then. Yeah, so thank you, Koji, for the kind introduction. And since you have already introduced us, then we will not repeat the same information again. But Kaustav and I, we both work for the Sensing and Measurements team here at PNNL. And that is why our presentation today will concentrate a little bit on how measurement-based studies can complement model-based studies to understand the evolving dynamics in the power grid, in the evolving power grid. Okay, sorry, I forgot to go full screen. So I'm going to start with a short description of where we work. So that is the Pacific Northwest National Lab. For those of you who are unaware, the US Department of Energy operates 17 national laboratories in the nation, and PNNL is one of them, located here in the red circle in the Northwest, as the name suggests, in Washington. So our headquarters is in Richland, Washington, so not the image that the Pacific Northwest generates. So we are on the dry side of the state, on the eastern side of the Cascades, but we also have offices and locations. We also have locations in Seattle, Portland, and then in Sequim, which is on the coast of the western coast of Washington, where PNNL conducts some coastal research. The National Lab has around about 6,000 staff members. So we do research on a lot of different topics aside from just the power grid, although I think Kaustav and I are more aware of what is going on in the power grid space, but the lab does more stuff. So PNNL is a leading center for scientific discovery in chemistry, data analytics, and earth science, and then for technological innovation in sustainable energy and national security. And the kind of mission that the lab tries to address is lies at the interface between the industry and the academia. So to make sure that cutting-edge research going on in academia makes the transition from being a purely theoretical concept to actually being applied in the field and making an impact. And similarly, making sure that academic research is informed by the challenges and the opportunities that the industry faces today. And we hope that we'll be able to bring a little bit of that flavor in our presentation today as well. So at the risk of, I'm sure like most of you are already aware, but I'll still just repeat that as the grid is being decarbonized, and with the increasing penetration of inverter-based resources getting connected to the bulk power grid, the dynamics of the grid is changing. The decades of experience that operators today have of how to operate a grid with synchronous generators needs to evolve, and we need to understand how the dynamics of a grid with both synchronous and non-synchronous generators is going to look like, so that the grid continues to be operated in a reliable and resilient manner. And there have been a lot of reports and papers and discussions on how the changes in a grid with growing IBR penetration looks like. And then one of the things that is brought up usually is with pockets of inverter penetration. The grid strength is reducing, there is loss of rotational inertia, and that is changing how the grid is going to behave. And some of the system reliability concerns that are also being faced because of IBR performance issues include their inability to ride through faults at times, nuisance tripping that leads to sudden unexplained generation loss in the bulk power grid, control oscillations, etc. And so I have put some links to recent reports by North issuing a industry-wide alert about these operation issues that the inverters are facing out in the field, and why the industry needs to make concerted efforts to address these issues so that the grid is continued to be operated in a reliable manner. And another very recent report that was released by ESIG this month is this diagnosis and mitigation of observed oscillations in IBR dominant power systems. I would encourage, if you are interested, to check out these reports. These have a wealth of information about the kind of issues that power grid operators are facing. And if you're observing something, what are the, people usually have an intuition of why something is happening, but these reports can help have a systematic analysis of, okay, if I'm observing this, why is this happening? What can be the potential mitigation? What should I take care of? And so on and so forth. I'm going to talk a little bit about the oscillations and the different types of oscillations and the different types of oscillations that the IBRs are introducing in the system, and how, so I'm specifically going to talk about the phasor measurement unit data. So I'm sure, again, you are aware, but phasor measurement units basically provide high resolution, time synchronized snapshots of electrical phasor quantities, and they help in providing a diagnostic tool of what is happening in the grid at the fundamental frequency, and basically gives a much better understanding of the dynamics compared to SCADA. So the observed oscillations that are being reported today, they have diverse characteristics and root causes. So there are subsynchronous oscillations arising due to interaction between inverters and say wind turbines or other grid elements. So for example, there have been oscillations reported when wind turbines have been left connected radially to a series compensated line. Then there are forced oscillations that are arising due to improper control logic. So sometimes something we would call low tech, that the units are fine, but maybe the plant control logic is providing erroneous time constants or erroneous reference commands to the individual plants, which is causing the units within a plant to oscillate against each other, and that is introducing oscillations in the system. And especially if the frequency of these oscillations are close to the electromechanical ranges, so between 0.1 to 1 hertz, then sometimes these oscillations are spreading throughout the system, creating wide area reliability issues. And improper control parameter tuning is also introducing some of these oscillations. So some aggressive control actions, such as having gain values too aggressive or time constants too aggressive, these can also lead to oscillations. And that is not a IBR specific issue. If we have improperly set or too aggressive control actions for synchronous generators, then they have in the past introduced oscillations in the system as well. And another way the IBRs impact oscillations in the interconnections in the power grid is they may impact the prevalent inter-area mode. So for example, if the inter-area modes that are present in the power system today, they are mostly influenced by where synchronous generators are located and how groups of generators are exchanging energy among each other at a low frequency, and those appear in the system as low frequency oscillations. But if suppose synchronous generators in particular areas are being replaced with inverter-based resources, then the loss of rotational inertia can change the properties of these modes. And because these modes have been studied, so the monitoring and control actions that are in place today with these operations that may need to be re-evaluated. So I'm just going to start with some examples of like this is already happening. So this is a recent example from the Western Interconnection, and this was reported by the Salt River project in Arizona. So basically what happened was a solar and battery plant in Arizona due to erroneous control logic. And this happened in September as well as November 2023. So the oscillations are pretty recent. So due to erroneous reference points being fed by the plant controller, the units within the plant, they injected oscillations at around 100 megawatts and 0.25 hertz into the system. And because 0.25 hertz is close to an inter-area mode in the Western Interconnection, so it is close to the North-South A mode. So that is why there was an interaction between, because this oscillation was a low frequency, this oscillation, which was injected by one plant in Arizona, was observed throughout the Western Interconnection. And the figures to the left are what SRP saw. And then the figure to the right shows basically what was seen in the control room of BPA, or Bonneville Power Authority. They are a transmission utility in the Northwestern region. And they saw that they have a mode monitoring scheme in place at their control room, and they saw that due to the presence of the forced oscillation, they saw underdamping issues in the North-South A mode, which is indicated here by these red lines. And so coordination was required among the different system operators to identify, okay, what I'm observing, is it really a underdamped natural oscillation that may lead to 1996 like outages, and so we need to take control actions, or whether it was a forced oscillation. So the crux of the matter is that inverters are able to introduce oscillations in the system through a wide range. So not only high frequency oscillations, but also low frequency oscillations. And a similar report, a similar event again was reported by California in, I think this was in 1 year ago in 2021 or 2022. Similarly, again, a battery plant introduced around 0.25 hertz oscillations from Southern California. So here, this is the RTTMA snapshot that CAISO had. So the source region was in Southern California, but it showed up throughout the system. And basically due to interacting with, again, the North-South A mode, the oscillation which generated in Southern California propagated throughout the entire interconnection. And the root cause here was some network connectivity issue leading to improper actions by the control logic software. In both of these cases, the inverters were grid following. So one question arises here that if instead of grid following inverters, we install grid forming inverters, are these observed issues going to be fixed? So the answer is yes, some of them may be fixed, especially the ones related to grid strength. Yes, with grid forming inverters, some of these issues will be fixed. But issues arising due to improper plant control logic, or say with grid forming inverters, for example, if you are looking at, say, virtual synchronous machines, where where setting the inverters is more complicated than, say, Drupe-based grid forming inverters. So the more complicated the logic, the more difficult it is to set parameters or tune parameters, and that may lead to issues again. So here is an example from, and this analysis was done by NREL, and I have put a link to the papers and the presentations on the slides as well. And this is observed in an island system, the Kauai Island in Hawaii. They had 4 IBR plants, and so I think again this one is pretty recent. It was reported in November 2021. Loss of generation of about I think that was about 20 to 30% of the island's generation that was being provided by this one synchronous generator plant. So that was lost, and then the IBRs responded to it, and that led to around 18 to 20 hertz oscillations that lasted for quite some time in the system. And while this was reported, one of the IBRs was already grid forming, and 3 of them were grid following. And so when NREL did this analysis, they proposed a number of mitigation methods informed by the EMT simulation of the system. And one of the proposed methods was converting existing GFL to GFM inverters. So that was done. One of the IBRs was converted to GFM. So then what they observed is a year later, with the GFMs, and these were virtual synchronous machines, the 2 GFMs start oscillating against each other at around 1 hertz, so at a slower frequency. But here the magnitude of the oscillation, the amplitude of the oscillation was much lower. So what I'm trying to say is that there is no like one answer. So it's not just the inverter properties, it's how the inverter is going to operate in the system, or how the inverter is going to interact with the system. So some of these issues may be diagnosed through model-based studies, but as we all know that models are not perfect. So having field measurements helps to diagnose some of these limitations that model-based studies may have. And then by having model-based studies and measurement-based studies go hand in hand, we can understand more about what is happening in the system, how to diagnose issues early, and how to mitigate them in an early enough manner. So here I'm going to talk about one of the studies that we did here at PNNL. So this was a model-based study of trying to understand that what is going to happen to the inter-area modes in the Western interconnection if all of the synchronous generators, which are fossil fuel based, are replaced by grid-forming inverters. So that is what we did. So we created 3 scenarios where we gradually increased the amount of inverter penetration in the Western interconnection. So first we replaced all the coal-based generation in WEC with GFM inverters, and that increased the GFM penetration to about 20%. And then we went on replacing natural gas and nuclear generators both. So after all these replacements, so the synchronous machines that are left in the system are basically the hydro-based generators. And here we have the map of the hydro-based generators in the WEC, and you can see that the large hydro generators are clustered around northwestern Washington, around basically the Columbia River, and also in BC Hydro in Canada. So what we observed, and here you can see on the left table, these are the known inter-area frequencies ranges that we have in the Western interconnection today. And I'll draw your attention to the 0.35 to 0.45 hertz mode, which is the north-south B mode, where basically Alberta and swings against northern US plus BC, and that area also swings against the southern United States. So this is a widely visible mode and of concern to system operators in the WEC today. So what we observe is that once we replace these fossil fuel-based synchronous generators with grid-forming inverters, so the geographical spread of these modes, they kind of shrink. So what we observe is that in scenario 1, where we only replaced the coal generators, so there were some natural gas and geothermal generators left in California. So we observed that so the Northwest and the generators in the BC Hydro, they are still present and they're swinging against each other. And as we keep on increasing the inverter penetration, because the hydro generators in the Northwestern cluster is not changing, so so initially with that drastic change of replacing all the coal generators, the frequency of the north-south B mode, so to say, so which does not exist anymore because it's not system-wide, that increases quite a bit. So the frequency increases to 0.69 hertz, and with the further changes also, the frequency shows a slight increasing trend. So now we have a mode around 0.7 hertz. And what we observe is the generators in British Columbia are swinging against those in the US Northwest. But obviously, this study has a lot of limitations. For example, we were not changing the power flow case, but as we can imagine that when more and more solar goes up in California, so maybe how the power flow looks like today is not going to look like the same. And then we also assume that whatever generator we were replacing, the amount of generator injection is not going to change with inverters. But again, like realistically, that is not going to be the case. So although this model-based study gives us an indication of what might happen, it is limited because we cannot simulate all possible scenarios and all possible heterogeneous fleets of inverters that might show up. So we did another measurement-based study to understand to complement what the model-based observations are showing. So this study now is not in the Western Interconnection; it is in the Eastern Interconnection. But the conclusions kind of validate what we are observing in the West with model-based studies, and it also shows that right now in the Eastern Interconnection, because the renewable energy penetration is not very high, so what we observe today cannot be directly interpolated. So we still need model-based studies, but through periodic measurement-based studies like this, we can keep an eye on, okay, what is going on in the system and how long are the model-based conclusions and the measurement-based conclusions in concert with each other. So this is an outcome from a project that we had with EPG. We deployed something called ESAMS, or the Eastern Interconnection Situational Awareness Monitoring System in the Eastern Interconnection, and PMU data from around 7 reliability coordinators were streamed to a central location, and we did oscillation monitoring. So one of the aspects was setting up mode meters to observe, to track the properties of 2 inter-area modes in the East. So it was, as the maps show here, the Northeast Midwest mode, where the Northeast in the, so basically from these maps, you can observe that the red generators are swinging against the blue generators. And the frequencies of both these modes are around 0.25 hertz, and they are typically well damped. So the damping ratio is around 10 to 15%. So what we did is we got these about a year of continuous mode estimates from the project. And then we took hourly averages of system conditions from the US EIA website, and then we tried to investigate whether correlation exists between the observed frequency and damping ratio estimates of the mode and the changing system conditions. So we selected 2 particular system conditions, the load, so how the frequency and the damping ratio varies with system load, and how it varies with renewable energy penetration. So again, there are limitations because the reported renewable energy penetration is only what is being metered, so the utility connected ones, and we don't have any visibility of behind the meter resources. And typically, all of the reported scenarios where the renewable energy penetration was less than 10%. So the variance in the data, the variance in the frequency and damping ratio with less than 10% renewable energy was more visible compared to higher renewable energy penetration scenarios. But our study still revealed that we can find evidence that, and so the gray points here show what was observed, and then the colored plots show what the quantile regression model learned and what the predicted outcome at different quantiles were. And we can see that we observe a close enough match. And then we can see that, with increase in system load, the mode frequency goes down, the damping ratio goes up because more synchronous generators are online. And similarly, with increasing renewable energy penetration, we saw that the damping ratio tends to decrease while the damping ratio tends to decrease while the frequency tends to increase. And this is something similar that we observed from the model-based study in the Western Interconnection as well. And then for the northeast-south mode, we could not find clear evidence of something similar. And one reason was because if you look at the southeast-eastern interconnection today, the renewable energy penetration was really low. So the key takeaways from the study was that obviously granular data sets of mode estimates, which were available only through PMU data being installed and streamed to a central location. And such granular data sets of mode properties were not available before for the Eastern interconnection, but being able to collect these measurements enabled us to study the impact of how the system conditions are influencing the mode properties. And we found evidence that for one of the dominant Eastern interconnection modes, as the renewable energy penetration is increasing, we can see the frequency increase and the damping ratio decrease. So although grid stability concerns are not immediately visible, if, say, there are light load conditions coupled with high renewable energy penetration in the future, then the properties of the modes should be monitored for potential underdamping. And again, like and probably as the renewable energy penetration in the northeast, in the southeast grows, probably the impact of RE penetration will become visible on the northeast-south mode properties as well. So periodic monitoring is necessary. And again, just to repeat myself, the model-based studies and measurement-based studies go hand in hand and will allow diagnosing what is happening in the system. So with that, I'll hand it over to Gustav.
I'll share my screen at this point and continue from where Shuchi has left. Okay. Can you see my screen? Okay. So Shuchi has given a good introduction on why we need phasor measurements and how they are helpful in monitoring system events, particularly oscillations. At this point, I'll change gears and I'll talk about what limitations phasor representation brings in and situations in which PMU data might not be adequate in understanding system dynamics. Of interest particularly are monitoring of disturbance events, wherein the data is highly non-sinusoidal. So one limitation of phasors are that they're defined only for sinusoidal quantities. So you have a sine wave with an amplitude, phase, and an angle. You get those critical parameters and combine what is called a phasor. Now that is a good representation as long as we are in the ambient period, because ambient data is sinusoidal, largely sinusoidal as we know. But as we move into disturbance events, the waveform gets distorted and we introduce non-sinusoidal features. And the phasors that we are estimating out of those non-sinusoidal windows might not be very reliable. So what is the point of understanding an amplitude or a phase when your waveform is undergoing rapid distortion, as you can see here? So there are two particular instances that I have reported here. One is from the well-known Blue Cut fire incident, which happened in 2017, leading to multiple IBRs getting tripped. And the other is from a particular event reported in the Grid Event Signature Library, which is an actual field measurement. In these two particular cases, if we are interested in understanding what went for those particular events in those time windows, our understanding is that the PMU data might not be very good indicator. So what should we do? Other than the disturbance events that I talked about, there are also instances where PMU data might not be a good representation, particularly when we are monitoring high frequency transients. Now, the PMU data, because of its inherent reporting limitations, which may be 30 frames per second or 60 frames per second, can only report frequencies up to its Nyquist reporting rates, right? So anything above that won't get reproduced faithfully. Also, these devices themselves have filters which kind of cut off frequencies above a certain range. So you are kind of limited to be monitoring somewhere around 5 Hz or below. So anything which has higher frequency in its waveform will not be reproduced. And this becomes important as we keep on introducing IBRs and they introduce subsynchronous and supersynchronous oscillations in the system. Okay, now, sorry. Okay, so with that, one way that we can navigate this problem is by introducing higher resolution measurements, including direct waveform measurements from the points of interconnection of these devices. Now, NARC experience while analyzing or doing postmortem analysis on these particular mini IBR trip events of last few years, like Blue Cut Fire, Odessa, and the others, they have seen that there was like the availability of data from these resources were not very ample. So, and the quality of the data was also not very good. By quality here, I mean the time resolution, time synchronization. So they kind of came up with this recommendation on what should be the reporting requirements from these resources, which includes PMU data, high resolution PMU data. And besides that, there's also recommendation on including point and wave data or waveform measurements. Now, in our community in power systems, there's some confusion or rather lack of consistency on what these measurements should be called. Some people call it points on wave measurements. Some people call it direct waveform measurements, synchronized waveform measurements. So they're all the same thing. So for today's talk, I would interchangeably use point and wave data and waveform measurements. Now, how are these waveform measurements important and why are they important? So I have this actual field data from a local PV facility in Richland, and this is one where the PV trips following an event. Now you can see by looking into the waveform data, we get particular insights into what happened just preceding the event and after and leading to the event. So you can see that there was a current from the PV was forced to 0 quickly after a short circuit event here. And then after that, we see transient over voltages in the voltages. And then there was also a restrike in the current followed that. So these are all signatures that help us understand what went into the PV to trip and what are the signatures or the patterns that we can learn from these events. Now, as we talk about waveform measurements, it's also important to understand what practices are there for currently recording and reporting point-on-wave data. So most of us are aware of digital fault recorders. So these are kind of the basic units which are capable of recording point-on-wave data as of now. So they are kind of mostly trigger-based devices. They have preset triggers for events like low voltage, high current, very like they are signatures of short circuit like events, and then they record that event for some duration, and then you have manual polling of the data from these devices from time to time whenever it's needed. Now, there are also challenges associated with this. First, that the triggering conditions are very restrictive, that you have to know what you are trying to record, and then only you can set the device to record that. Now, with changing signatures of the disturbance from introduction of IBRs, that might be very challenging, that you might not know exactly what you are looking for in the data. With that, there has been a considerable discussions and interest in the community on what we can do with continuous point-on-wave recording and streaming. Like we have the data for entire duration, and then we can look into it and find out of what you want to do. Now, the primary limitation or challenge of continuous point-on-wave recording is that the infrastructure at most transmission operators does not support continuous streaming of point-on-wave data. This would entail large bandwidth requirements and large storage requirements, which most transmission operators are not very sure about of making that investments at this point. So here you can see a snapshot from a report from Dominion Energy that they compare between synchrophasors and then continuous and triggered recordings of points on wave. You can see that for a single day with the 72 channels, this entails like about 95,000 megawatts of data, which is huge. And this data then also has to be transported from the substation to the control center, which is a challenge. Instead, as we have already been doing, is what is a triggered point-on-wave data recording. But with that, one caveat is that the triggering condition has to be agnostic to the knowledge of the event signatures. Like it has to be more generic, that you can record a larger set of events without exactly knowing what you want to record. And with that comes the objective of streaming this triggered point-on-wave data. So we will, in this presentation, I will talk about this both aspects. Like we'll focus on how we can make the triggering condition very generic, just to record every non-sinusoidal event signature. And then I'll also give a sneak peek into how we can like transmit the data intermittently. So a quick primer on what we are trying to do here. We are trying to record short duration point-on-wave data under situations when PMU data is not reliable, which is basically saying that wherever the waveform data is non-sinusoidal. These are particular disturbance events that I'm looking for, because my interest is kind of disturbance analysis and monitoring. So what we do, we use a phasor estimation algorithm. Any off-the-shelf curve fitting based approach works fine here. We mention of one particular approach here, but the others are as good. Now, once we have those estimates of the phasor amplitude, phase, and the frequency, what you try to do is that you try to get this goodness of fit error between what your measurements are and what your estimated model is saying. Now, if your actual data is a sinusoid and what you're trying to estimate is also a sinusoid, then you would get a low error on these measure. But if your data starts deviating from a sinusoidal model, then this error would go high. So this would be a good indicator for us to know whether we are estimating sinusoidal quantities or are we deviating from that assumption. So with that premise, this is the broad framework of what we are trying to do. So you have your continuous waveform measurements at the grid edge. You take in to do phasor estimation on it. You get PMU data. But besides that, you're also getting this goodness of fit error. Now you compare that goodness of fit error with a threshold, which you have pre-decided or preset. Now, if that error is high, it's an indication that your data is non-sinusoidal, and therefore PMU data might not be good enough by itself. So you need to complement it with something else. And that complement is coming from point and wave data. So you kind of have a condition-based switching, a condition-based reporting here. So if this threshold goes, if your error goes higher than the threshold, then you kind of close the switch and your point and wave data is also recorded and reported to the control center. How we do that streaming, I'll come to that later. But that's what gets reported at the control center. So you have continuous streams of PMU data and then short bursts of point and wave data, which are then analyzed for disturbance signatures. So here is an example. Again, we picked an real field measured waveform data from the grid event signature library. And this is basically showing that whenever your data is in ambient conditions, sinusoidal, you do phasor estimation and you also do the goodness of fit calculation. Your goodness of fit calculation is below the threshold, so nothing of your point and wave data is being recorded and reported. But as long as as you have this even your error going higher than the threshold, then you are kind of triggering the recording of the point and wave data. So this is your phasor data, which is being reported at the control center, and this is your point and wave data, a short duration that is being recorded and ready for transmitting. So this video will also talk about the same thing. So you can see at this point your data is ambient, nothing is being recorded at the control center, but the moment you see that there will be an event, and then the LSC value will go high. You can see here the LSC value goes high, and then this is the duration in which your data has been recorded for and ready for being reported. Okay, now what are we doing in terms of streaming this measurement? So as I mentioned, the main bottleneck in streaming the data is its bandwidth and also in its capability of storage and so for the storage, we have kind of addressed that issue by saying that we are only doing a trigger-based recording and then streaming it whenever it's required. But for streaming the amount using the same bandwidth, what we kind of do is that we kind of use the same infrastructure as the PMU data is being used for reporting. But instead of continuously streaming the point and wave data, we kind of break that into small sized packets with serialized timestamps and then stream this data in the idle periods between the PMU transfer. So if you have a few packets of your PMU data which are being streamed, and then and there are idle periods between that streaming, use those idle periods for streaming point and wave data. But that data is then not streamed continuously, but then they're streamed intermittently and then spread over a longer duration. In any of these streaming, PMU data is given the priority, and point and wave data is given the second priority because point and wave data is not indeed used in the real-time monitoring, but for post-mortem analysis of events. So the idea is that this new data transfer protocol that has come up and has been standardized by IEEE is called a streaming telemetry transport protocol, or STTP. This can facilitate this kind of data transfer. This is a variable configuration protocol, not a frame-based one. So you can basically package different data types and then send them, and the headers can specify what you are sending. This is a publisher-subscriber kind of a model. So more on that we can talk later, or we can have other presentations talking about SDT. So quickly, I will then move on to what we are doing with that data at the control center. So disturbance analysis at the control center, as I mentioned, will use both continuous PMU data as well as event-triggered point and wave data. The way we are seeing the application is that it has to have two different layers. The first layer, or the high-level layer, is using PMU data to identify occurrence of the event and just the nature of the event. So if it's a event like a IBR trip or something, you can just see the phasor measurements of the current from the points of interconnection and say, okay, there's been a trip. Now, the detailed information layer is where we use the point and wave data to complement PMU data in the root cause analysis of the event. So this is where basically the postmortem analysis is happening. So you get the detailed signature from the waveforms and try to understand what led to that IBR trip, or what was the events that was leading, or what was the preceding signatures that finally happened to lead the IBR trip. So one example that I put here is a disturbance event in which an IBR trips. So as I mentioned, the occurrence of the trip can be identified from the PMU data. The point and wave data can identify if the trip was due to violations in the instantaneous quantities. So you can have instantaneous over voltage that can lead to the trip. You can have instantaneous over current that can lead to the trip. So all these things might not be observable in PMU data. But if you have a point and wave data available at your disposal, then you can look into and dig to understand what exactly happened. Another important feature that can be utilized is that you can do right to compliance testing for this. Like, all these IBRs have mandates on what their write-through performance should be. Like, these are specified for both voltage and frequency, or voltage both in terms of RMS quantities as well as instantaneous quantities. So you can check whether a trip like the one that I showed was that legitimate trip because of the violations of the voltage and currents being outside the permissible limits of right through, or was it something that was not allowed and the IBR anyway tripped, which can be used for flagging nuisance trips. So all this analysis can be performed if we have the high resolution point and wave data at our disposal. So here I put an example. This is a simulated an EMT simulation of a PV trip due to a fault in one of its neighboring buses. So what we see here is the voltage and the current waveform measurements. Again, the phasor data for these event captured, as well as the event triggered point and wave records using the method that I was mentioning. One interesting observation to make here is that there is a transient overcurrent in one of the phases, which is not captured in the phasor measurements. And this is what we will analyze more as we see. So this we built a platform kind of in MATLAB just to analyze it and to see what write-through compliance is happening here. So as you can see here, we have one specified functionality to check for whether it's a trip or a no trip, which gets red means it's showing us there's a trip, which is very easy to pick from the current measurements alone. But then what is more complicated and involved is to see what led to the trip, or if the trip was within the write-through performance mandates. So we kind of have the requirements here as per the IEEE 2800 write-through requirements, which are kind of saying whether the voltage was within this or outside this magnitudes for this time duration, and same with the frequency. And then everything here green indicates that the performance variables or the monitoring variables were within the write-through requirements, but we still see a trip. So which kind of flags that, okay, so this was a nuisance trip. So the IBR was not supposed to trip, but it still tripped. So this kind of flags and kinds of helps operator inform the manufacturer or someone else operating the plant that, okay, something might be wrong with your relay setting. So you probably need to go back and check or probably retune it to match the write-through requirements. In this particular case, it was a transient overcurrent in one of the phases, which was not adjusted or not accommodated as per the write-through requirements. Okay, so this is one of the use cases that I mentioned of where we can use high resolution point and wave data. With that, I will conclude my talk. The few takeaways that we can have from here is that phasor measurements are not always reliable for monitoring non-sinusoidal disturbance events. To complement that, point and wave data can offer deeper insights into disturbances. In that context, continuous streaming of point and wave data may not be very practical. So we talked about an automated approach for recording short duration point and wave data for disturbance events. The triggering condition is agnostic to the event type, but relies identification based on non-sinusoidal signatures. So what we did was that we transported short bursts of event-triggered point and wave data intermittently during the idle times of PMU data transfer, utilizing the same communication infrastructure, but a different protocol. The disturbance analysis at the control center, you can utilize both the existing continuous streams of PMU data that we have, as well as the short duration event-triggered point and wave data. This can support root cause analysis and also help in checking for right to compliances. With that, I think I'll stop and I'll be happy to take questions, both me and Shuchi.
Thank you, Shuchi. And then, so if you have questions, yeah, we have like a more than 15 audiences in total. So please type your questions in chat window. Then, the speakers can read the questions. And in the meantime, I have just one or two like fundamental questions. So the Shuchi, you mentioned about the erroneous control logic in your presentation. So the erroneous control logic means like a high gain or also like a short time constant. It is, am I right?
So it can be both. So so there are two aspects here. So of the industry experiences, the events that I talked about, some of them were faulty plant control logic. So not the unit controllers themselves, but so suppose for one IBR plant, there are 4 particular units, and then there is a secondary level plant control logic, which feeds reference set points to 4 of the IBR individual IBR units. So say the controllers of the individual IBR units were fine, but the problem was in the plant control logic. So it set bad inputs to the 4 units, and that resulted in a faulty operation that introduced
I see.
the oscillation.
Okay. So we have 2 possibilities. Okay.
That is possible, but also improper control parameter tuning for say the PF droop or the QV droop, including wrong droop parameter settings or too aggressive settings. So because the faster you respond, the faster you try to respond, the probability of improper interactions grow. So those aggressive actions, those aggressive control actions can also introduce these kind of oscillations. And the reason I specifically mentioned time constants was that, so if you noticed both of the examples that I mentioned for the Western interconnection, and this is kind of a speculation, but both of them were at 0.25 hertz. So had they not been at around that frequency, they would probably not interact with one of the north-south modes and pose wide area reliability concerns. But say if you issue commands, if you issue set point commands exactly after every 4 seconds, then any problem, any misoperation there would introduce an oscillation at 0.25 hertz and pose more of a danger to the system than had it been at any other frequency. So anywhere there is a possibility of setting improper control parameters, anywhere there is a possibility of malfunction. So the more complicated the logic, the more parameters you need to set, the more instruments or the more devices that are involved in the control, the more the possibility of like erroneous action leading to oscillations, or even say other reliability concerns like nuisance tripping or other dynamic issues.
Okay, thank you. I think we have one question. Oh yeah, you have already responded it. Okay. So, and then the next question is, in the case of WCC or in Eastern interconnection studies, did you use phasor models, or did you happen to use EMT model? Because you use the EMT model for Hawaii Island, but in the case of Bark power system, it's very
Yeah.
difficult to use EMT models. So
Right. Yeah, so all of our studies on the WEC were on PSSE, so using just the positive sequence models. I don't think we can solve any EMT model for WEC with our current infrastructure. And yeah, so I'll again just clarify that the Hawaii study was done by NREL, and the material that is in the slides today is just reproducing their work, but that they did in fact do an EMT study because it's an island system, so with so much limited insights compared to something like WEC. And that is why, like complementing model-based studies with these kind of measurements is important, because it is not realistic to expect that we can create EMT simulations of WEC and then run all possible scenarios and then, find what is going to happen in the system as the IPI penetration is growing.
yeah, I understand that. But in the case of like the Hawaii oscillation event, the major frequency component was around like a 0.5 hertz or something, right? In this case, do we really need EMT models? For example, if we simply use a phasor model, can we also represent this kind of like a low frequency oscillation?
Yeah, I think with low frequency oscillations in the electromechanical range, yes, the positive sequence models are enough, but maybe yeah, the higher frequency subsynchronous kind of oscillations or even control interactions in that kind of frequency range would probably need EMT simulations. And one of the findings from like these NERC suggestions is that EMT simulations might uncover hidden failure issues, especially in areas where there is a lot of IBR in the grid. So like those areas may have grid strength issues and other kind of and because the frequency the actions there can be faster. So because of that time scale separation, they might interact with some of the other grid elements that are not usually modeled in say PSSE, say the transmission line dynamics. Those are not probably modeled in high fidelity in some of our positive sequence studies. So where risks due to those interactions may be apparent, so there we would need EMT simulation. Kostov, do you want to add anything to that?
No, I just wanted to add to the capabilities here that at PNNL we do have capabilities of studying micro-WEC systems. Like this is a smaller version than the mini-WEC, which is having its PSCAD model for simulation, and we are working on that actively. But so that's one perspective of the problem, but that still does not take into the full glory of the system. The other approach that we took at PNNL was that we kind of did hybrid simulation. So as to the IBRs that we are more focused on studying, we had a detailed PSCAD model, and then for the entire system had a PSSE-based model, and there was an interface like a ETRAN or something which could let them talking to one another. But that was not used in this particular simulation that Shuchi presented. But in terms of capabilities or studying simulations or studying oscillations of higher frequency nature, we can probably investigate this. One important aspect of high frequency oscillations is that they're kind of localized. They're not system-wide prevalent like inter-area oscillations or wide area events. So it might suffice to do EMT model of the neighborhood of the plant that we're trying to do, or few nodes away from it, should suffice for studying those subsynchronous kind of events or something else.
Thank you. So basically, converter-driven oscillation can be treated as a local event.
Yes, typically they are not as wide area as we would think for the inter-area events.
Yeah, of course, I understand that this is not like a grid-wide event, but for example, the Shuchi introduced like the historical event in Arizona state, and that is the typical converter-driven oscillation event. And then if, for example, if the oscillation can be observed in, for example, entire Arizona state, do we still think that is like a local event, or no, this is a wide area, right? Actually, the impact area is wide.
So that is why I included those two particular examples, because although they were introduced by converters, they were in fact observed throughout WEC. So not just within Arizona, but also in Washington and Oregon, and same for California. It was visible throughout the system. And the reason it was is because the oscillation frequency was low, 0.25 hertz, which is in the inter-area range. So one of the things about the IBRs is that they can introduce oscillations in a wide range, including from the inter-area range to the higher subsynchronous range. So but you will also observe that these converter-driven oscillations, which were at lower frequency, which in that inter-area range, they were not like because of like the converter physical behavior, but more due to the control logic issues. So imagine for a synchronous generator, maybe those are like maloperating steam valves or something like that. So these kind of fluctuations or or like rogue inputs can also happen at synchronous lamps. So this is not like a converter physics issue, but a control logic of the plant operator issue, which resulted in that 0.25 hertz oscillations that spread throughout the Western interconnection.
Right.
But because so I would just like to add that because the operator's knowledge about these how these converter controls operate at these both levels, that the individual unit level and also at the plant level. So as the industry is learning more about it, more and more issues are being observed and reported, and it will take some time to understand, like, okay, what exactly is going wrong. And I have had this discussion at different like NASP and other industry forums, and people have reported that although like the frequency is similar, and probably even if the oscillations are being introduced by the same plant at different instances, the issues are all different. So even though they are doing like installation and commissioning tests and other things, something or the other is escaping, and then it is becoming apparent only after some time. And maybe some of these issues, they become apparent only in particular grid conditions, and so they are not visible in the installation and commissioning tests that you are doing. And in the Arizona case, that there was, which I found a little, like this is not something that you expect to cause like a area, like wide area event. It was a division by zero error in a controller. So yeah, that is not a converter physics issue. That is some kind of programming issue, right?
Yeah, exactly. So that particular event was mostly switching between the control logics, which led to a kind of a forced oscillation event close to the frequency range of inter-area mode. So it was more of a forced oscillation event than of an control interaction from system physics that she was mentioning. So yeah.
Thank you. Do you have any questions? I don't realize. Oh, there is one question in chat window.
Okay. So can you tell us when the degree of penetration of inverter-based renewables into the grid becomes a problem? So there is no one answer to it. And this is one of the conclusions from the study that I was talking about with the Western Interconnection Model-Based study that we did. So although there is obviously like a correlation between increasing inverter penetration and the changes in inter-area modes, when do they become underdamped or not. But the thing is not just like the absolute number. So there may be no problems even if there is like 50 to 60% inverter penetration in the grid. But what matters is where those inverters are being introduced. So for example, suppose you have a large source of synchronous rotational inertia at a particular place, and you replace that big generator with inverter-based resources which are not probably tuned properly, then that can become a problem. So it's not just like a threshold that, okay, if I have more than 20% inverter penetration, I should be ready for problems. It is also where those replacements are occurring, where is the IBR penetration taking place. If it is in a comparatively stronger grid area, then maybe those dynamic issues will not be that apparent as a similar capacity plant in a much more weaker area of the grid. All right. So yeah, so we don't know like one number or one issue. So it's different for different systems and depends on what kind of an inverter configuration, what kind of energy source, lot of different things. So, which is why this is such a difficult and interesting problem.
Thank you. I think that time is almost up. But anyway, I was personally impressed by the very solid converter-driven oscillation study regarding inverter technologies. And then I think the grid sensor is likely to be more available across the US in the future. And then we hope that we can aware hopefully the precursor of the undesired oscillation events more. But anyway, Dr. Shuchimita Biswas and then Dr. Kaustav Chatterjee, distinguished power engineers from the government-funded National Lab, PNNL. It was great to have you both at the IEEE 50th section webinar today. And everyone, our next webinar will cover a topic regarding grid-forming converter study in Spain in October. And the date and time are not fixed yet, but I will upload a flyer shortly once it is ready. And please stay tuned and enjoy the rest of your day. Anyway, thank you so much for the nice presentation today.
Thank you. Thank you for the
Hey,
invitation.
everyone. Thank you for your time.
Very much, Koji.
Thank you.